Hello students, welcome to my channel GVS Chem. In this module Biomolecules Part 2, let us discuss the ring structure of glucose and the structures of di and polysaccharides. Please subscribe to my channel, like, share and comment on my videos. Let us discuss the ring structure of glucose. See here, these are glyceraldehyde. So this glyceraldehyde, in glyceraldehyde, this is a primary carbon, primary hydroxy group. This is primary hydroxy group. Here also this is primary hydroxy group. And this is secondary hydroxy. Secondary hydroxy means this hydroxy group is present on the carbon which is adjacent to the primary hydroxy. Okay. So this is a plus glyceraldehyde. Plus indicates the dextrorotatory and L minus represents levorotatory. So these two forms of glyceraldehyde are optically active. Optically, so they are optically active. And here with respect to the CH2OH, with respect to this CH2OH, this hydroxy group is present on right side, and in this compound the hydroxy group is present on left side. Therefore, the compound having hydroxy group on right side, it is known as D plus glyceraldehyde. So this substance is D plus glyceraldehyde. Whereas here this is L minus glyceraldehyde. D plus glyceraldehyde, L minus glyceraldehyde. Please note that there is no relation between DL configuration and optical rotation. There is no relation between DL configuration and optical notation. So if OH group is present on right side, it is called D configuration. If OH group is present on right side, it is called D configuration, whereas if it is present on left side, it is called L configuration. Now the name of the glucose, the correct name of the glucose is D plus glucose. The correct name of glucose is D plus glucose. D plus glucose. How this D and L are assigned to other substances? See the plus isomer. Therefore, the plus isomer of glyceraldehyde has a D configuration and minus isomer of glyceraldehyde has a L configuration. Now, all the compounds which can be chemically correlated to D isomer of glyceraldehyde, all those compounds which can be chemically correlated to D plus isomer of glyceraldehyde are said to have D configuration, whereas those which can be correlated to L isomer of glyceraldehyde are said to have L configuration. Now let us correlate glucose to glyceraldehyde. So here in this figure, this is the glucose. So this is glyceraldehyde. In glyceraldehyde, the second carbon from the bottom has OH group on the right side. So for this also the second carbon from the bottom has a hydroxy group on right side. Therefore this is a D plus glucose. This is D plus glucose. So all the compounds are compared to D and L isomers of glyceraldehyde and respective configuration is assigned to such compounds. Now, the structure shown for glucose, see in the previous slide we observed the structure, and the structure shown for glucose could explain the most of the properties. So that structure could explain the most of the properties what we discussed in the previous module, but it could not explain some of the properties as shown below. The aldehyde present in the glucose should give positive shifts test. So what is the positive shifts test? So this is shifts reagent plus aldehyde should give magenta color. But in practice, the aldehyde present in the glucose does not give the shift test. Also it does not give the addition product with sodium bisulfate. So aldehyde present in the glucose should give the positive shift test, but in practice the glucose does not give the positive shift test, and also it does not give the addition product with bisulfate. Not only that, the pentaestate of glucose does not react with hydroxylamine, indicates that the absence of free group. So if aldehyde group is present, this is C double bond O plus hydroxylamine NH2OH. So here this must react, this is removed as water, and therefore we get C double bond NOH. So this is hydroxylamine. So if aldehyde present in the glucose should give this product, but in practice it is not giving. Therefore this indicates that whatever the aldehyde group present in glucose, it is not in the free state. Glucose is available in two forms, that is alpha form and beta form. Alpha form of glucose with a melting point of 419 Kelvin is obtained by crystallization from concentrated solution of glucose at 303 Kelvin. On the other hand, beta form of glucose with a melting point 423 Kelvin is obtained by crystallization from hot and concentrated aqueous solution of glucose at 373 Kelvin. Therefore, these two forms are obtained by crystallization at different temperatures. So this behavior could not be explained by open structure shown previously in the first slide. Therefore, it is proposed to have a ring structure. So it was proposed that one of the OH groups may add to CHO group, that is aldehyde group, and form a cyclic structure which is hemiacetal in nature, hemiacetal structure. In the cyclic structure of glucose, it was proposed that the OH group present at C5 carbon undergoes cyclization with aldehyde group. So here, this is the open structure. In this the numbering is given from top, that is carbon bearing aldehyde group should get the number 1. So 1, 2, 3, 4, 5, 6, and this is the end carbon, or we can say it is a primary hydroxy group. So the hydroxy group present at the C5 carbon undergoes cyclization with carbon, C1 carbon. So once this cyclic structure forms, we get two structures. These two structures differ at the configuration of C1 carbon. So here in this structure, the hydroxy group is present on the right side of the C1 carbon, whereas here the hydroxy group is present on the left side of the C1 carbon. Therefore, as a hydroxy group is present on right side, it is called alpha glucose or alpha D glucose, because with respect to glyceraldehyde we have already assigned D configuration to the glucose, because with respect to glyceraldehyde, hydroxy group is present on the right side. Therefore this is D glucose. So now at C1 carbon, the hydroxy group is present on right side, therefore this is alpha D glucose, and here the hydroxy group is present on the left side of the C1 carbon, therefore this is beta D glucose. Therefore here, so we can write, if OH group, so if hydroxy group is present on right side of the C1 carbon atom, it is alpha glucose, and of course already D configuration is assigned, and this is alpha D glucose. Since the optical activity is towards the right side, therefore it is plus. Totally it is alpha D glucose, and here hydroxy group is present on the left side, therefore it is a beta D plus glucose. Now here these two isomers, this left side isomer, right side isomer, they differ in the configuration of C1 carbon. So the two cyclic structures or hemiacetal structures of glucose differ only in the configuration of OH group at C1 carbon, and of course such carbon in which the hydroxy group differs in the configuration is known as anomeric carbon. Therefore, Two such isomers which differ in their configuration at C1 are called anomers. Whatever the cyclic structure we assigned in the previous slide, it is in a two dimension. So now let us try to assign the three-dimensional structure, that is for cyclic structure of glucose. So imagine this structure. This structure has double bonds here. Therefore here one of hydrogen, here it is one hydrogen. This is one, this is one. So here two hydrogens. Totally what is the formula? C5H6O. This compound is known as pyron. So this pyron can be shown in this manner, in a simple way. So this is pyron, right? Now, the structure of glucose is also similar to pyron. Therefore, here this is the pyron. So this is a six-membered ring in which the hetero atom, that is oxygen atom, is there. So in this structure, the structure of glucose, this is alpha D glucopyranose. Because this structure is similar to pyron, so it is referred as a glucopyranose. So this is alpha D plus glucopyranose. This is beta D plus glucopyranose. So this the numbering is given from here 1, 2, 3, 4, 5. This is the sixth carbon atom. So here see these two structures. In the number one carbon in alpha D glucopyranose, the OH group is present down below the plane of the molecule, whereas here the OH group is present on above the plane of the molecule. Therefore, this is alpha D plus glucopyranose and this is beta D plus glucopyranose. And these structures were given by Haworth, a scientist known as Haworth. Haworth structures. Now let us discuss about the fructose. Fructose ketohexose. Ketohexose. Keto means it has a ketone group. Now how fructose is obtained? Fructose is obtained by hydrolysis of sucrose along with glucose. So sucrose on hydrolysis, glucose plus fructose. So the structure of fructose is shown in this way. So here this is a ketone group is present on second carbon from the top. Therefore this is CH2, C double bond O, CH. Except this second carbon, all are in the similar way. So here now we have a 5-membered ring. Let us try to draw a 5-membered ring. That is, this is oxygen in this way. So here are double bonds. So this substance is known as furan. This substance is furan. So the formula of the furan is C4. Here is one hydrogen, C4H4O. So furan is. So the ring structure of furan is ring structure of fructose is similar to furan. So here this is the furan and here this is alpha D minus fructofuranose, because this ring is similar to the ring of the fructose is similar to furan. Therefore the ring structure of furan fructose is referred as a furanose. So this is fructofuranose and this is alpha. So the first carbon has this is the first carbon and then the second carbon. The second carbon has OH group on right side. Therefore this is alpha, this is beta. So in alpha isomer, the CH2OH, that is the first carbon present on the second carbon, is on the left side. Therefore this is alpha isomer. Whereas in beta isomer, the CH2OH group, that is the first carbon, is present on second carbon on right side. Therefore this is alpha isomer, this is beta isomer. Both are D configuration, because with respect to glyceraldehyde, the hydroxy group present on fifth carbon is on right side. Therefore this is a D. The Haworth structures of fructose are given here. So this is a furan oxygen. So with respect to this oxygen, this is the C1 carbon, 2, 3, 4, 5 and this is 6. So here in alpha isomer, the CH2OH is present above the plane of the furan ring, whereas here in a beta isomer, the CH2OH is present below the plane of the furan structure. Therefore, this is alpha D minus fructofuranose, and this is beta D fructofuranose. Now let us discuss the disaccharides. Disaccharides are the carbohydrates which on hydrolysis give 2 glucose units. So such hydrocarbons are called disaccharides. Disaccharides, the common disaccharides are sucrose, lactose, maltose, etc. Now let us discuss about the sucrose. So sucrose on hydrolysis we get glucose and fructose. So 2 monosaccharide units are joined together with an oxygen linkage. So 2 monosaccharides linkage, monosaccharide groups are joined together by an oxygen called, and of course this link is called glycosidic linkage. So if the reducing groups of 2 glucose units are involved in a cyclic structure, so if the reducing groups of both the monosaccharide groups involved in ring structures, it is called non-reducing sugar. Therefore, now let us see the structure of sucrose. So this is the structure of sucrose. Here, this is the glucose unit and this is the fructose unit. So in this glucose unit, this is the aldehyde group. Just remember how it is before the structure. So before the structure, it is like this. So this is aldehyde group is the reducing group. This reducing group is involved in the ring structure. Therefore, as this reducing group is involved in the ring structure, therefore this is no more reducing group. Similarly, in fructose also, this is the reducing group. So since this reducing group is involved in the ring structure, so this group is also no more reducing group. Thus, the sucrose is non-reducing sugar or non-reducing carbohydrate. So non-reducing carbohydrate means if both the reducing groups of 2 monosaccharide groups are involved in the ring structure, it is called non-reducing sugar. Now here this is the glycosidic linkage. So this glycosidic linkage is in between C1 carbon and this is C2 carbon. This is C1, this is C2. So the glycosidic linkage is in between C1 and C2. So glycosidic linkage is in between C1 and C2. C1 carbon of alpha D glucose and C2 carbon of beta D fructose. Sucrose, it is dextrorotatory. On hydrolysis of sucrose, it gives 2 glucose units, that is 2 monosaccharide units, that is glucose and fructose. So the glucose, after hydrolysis, the glucose so obtained is dextrorotatory with angle of rotation is plus 52.5 degrees. And fructose is levorotatory with angle of rotation is minus 92.4 degrees. So here, as that levorotatory is more, the final result is levorotatory. Therefore, after hydrolysis, the solution becomes levorotatory. Initially, it is dextrorotatory, but after hydrolysis, it becomes levorotatory. Hence, the sugar is called invert sugar. Now let us discuss about maltose. Maltose is a disaccharide made of 2 glucose units joined by glycosidic linkage by using C1 of 1 glucose unit and C4 of a second glucose unit. So this is the maltose diagram. Here C1 of first glucose unit is involved in ring structure as well as glycosidic linkage. Therefore, it is not free for reducing after dissolving in water. Whereas the C1 of second glucose unit is free. Therefore, when maltose is dissolved in water, this the C1 of second glucose unit may be available for reducing. Therefore, maltose is reducing sugar. Therefore, C1 of second glucose unit is free, and when it is dissolved in water, C1 of second unit becomes free, and hence it becomes reducing carbohydrate. After disaccharides, we have polysaccharides. Polysaccharides are those carbohydrates which on hydrolysis a large number of monosaccharide units. That means when these polysaccharides are hydrolyzed, we get a large number of monosaccharides like glucose, fructose, etc. So the best examples are starch, cellulose. Starch is the important foodstuff to mankind. So starch is available in many foodstuffs like rice, wheat, potato, and some vegetables. It is a polymer of glucose. What is polymer? A long chain obtained by combining a small units is known as a polymer, and of course the process is polymerization. Starch has two components, that is amylose and amylopectin. Amylose is a long chain polymer and amylopectin is a long chain and branched chain polymer. So amylose is water soluble. It is unbranched chains. Unbranched chains means amylose has all long chains. It has each chain has 200 to 1000 units of glucose, and it is the polymer of alpha D plus glucose units. And the glycosidic linkage is in between C1 and C4 carbon atom. So the glycosidic linkage is C1 carbon of first glucose and C4 carbon of second glucose. Now let us see amylopectin. Amylopectin is water insoluble. See here, amylose is water soluble and amylopectin is water insoluble. And it is branched chains. Amylose is a branched chain, unbranched chain, whereas amylopectin is a branched chains. And it has, see, so many amylose chains are branched with each other, therefore we get amylopectin. So this is also made of alpha D plus glucose units. Branching takes place at C1 of one chain and C6 of other chain. Now this is amylose. See here, this is first carbon of one glucose unit and fourth carbon of another glucose unit, and of course it continues in this manner. And this glycosidic linkage is referred as alpha link. That is, the glycosidic linkage takes place from down below the plane of the chain. On the other hand, this is amylopectin. So this is amylose chain and this is amylose chain, and both of these amylose chains are joined by branching here. This is C1 of one branch and this is C6 of other branch. So this is amylopectin. So if the glycosidic linkage is formed in between carbon atoms of two monosaccharides, that is from the same side of the plane of the chain, it is called alpha link. Now let us see glycogen. Cellulose occurs. Now let us see cellulose. Cellulose occurs in plants. It is abundantly available in the plant kingdom. It is made of beta D plus glucose units, whereas starch is made of alpha D plus glucose units. And the glycosidic linkage is in between C1 of one carbon and C4 of another carbon atom. Glycogen is the carbohydrate stored in animal body and is stored in, this glycogen is stored in liver, muscle and brain. When the body needs glucose, enzymes break the glycogen and down to glucose. Glycogen is also found in yeast and fungi. In the next module, let us discuss amino acids and their classification. Please subscribe to my channel, like, share and comment on my videos. Thank you.